All right, the last topic we're going to take a look at in this lecture is going to be that of forced convection over non-circular cylinders. So what is a non-circular cylinder? Well, it's a cylindrical object that it does not have round cross-section. It can have other cross-sections. So cross-section could be a square, it could be a hexagon, or a simple flat plate. It could be another example of a non-circular cylinder. And essentially what we mean that they're long objects that have cross-section, be it square, hexagon, flat plate, triangular, it could be another one. But really what this turns out to be is for any of these different shapes, we again have a correlation for Nusslet number that we can determine the convective heat transfer coefficient from. And the equation that we use is identical to the one that we saw for the circular cylinder that we looked at earlier, where we had C Reynolds number based on diameter and Prandtl number evaluated at the film temperature raised to the power 1/3. So what you'll notice here is we have C and I forgot something. I forgot the N. We have the power, Reynolds number raised to the power of N. And so values of C and N, these depend on Reynolds number. Well, first of all, they depend on the shape and the Reynolds number. So depending upon the book that you're using, you'll find tables that will have non-circular cylinders and they'll have different values of C and N. Just be careful to make sure that you're pulling the values at the right Reynolds number, and then from that you get C, you get N, and embedded within the Nusslet number we have the convective heat transfer coefficient, because remember HD over K, and if we're evaluating at the film temperature it'd be that. So what we're going to do now, let's take a look at what some of the fluid mechanics looks like with these different objects. And so what we have here are a set of videos starting with a circular cylinder, and there you can see the C and the N. For this one, the Reynolds number was around 550, so it's on the lower end. This is the flat plate, a very interesting flow dynamics downstream, massive separation, and consequently the C and N values vary from the front to the back. There we see a square rotated at 45 degrees. You get a very much different flow pattern downstream, very strong oscillations. There we see a hex and the specific C and N for the hex, and then the hex rotated at a different angle, and you can see again a very different dynamic flow pattern downstream. So the main thing here, just watching these different flow visualizations, you can see the flow over these different bodies is very, very different. It depends upon orientation. We can see by examining, for instance, the cube, when it's aligned one way or rotated, very, very different dynamics downstream, and consequently the C and the N values will change, which is what people would determine from experiments. And again, the main thing, be careful about the Reynolds number that you're applying these correlations to. If you're pulling values out of a book, make sure that the Reynolds numbers that you're using are the correct Reynolds numbers. So anyways, interesting flow viz. That is non-circular cylinders. The last shape that we're going to cover in this lecture are spheres. And again, there are different correlations that exist for spheres. I'm going to give you one. And this one applies for Reynolds number based on diameter. That goes from 17 up to 70,000. So again, be careful to make sure that it applies over the range. And for this one, turns out that the properties are being evaluated at the film temperature, which we saw earlier. T film was T infinity plus T wall divided by 2. And so anyways, that's a correlation that exists for a sphere, and you can see it's similar to what we saw earlier for the non-circular cylinders, but there are other correlations that exist. The main thing with any of this, pull out the right equation and make sure that you're evaluating properties at the right temperatures, because these are experimental correlations, and we have to apply them using the same conditions that the people who have collected the data did in the first place. So just be a little careful of that when you're solving problems in heat transfer. And with that, that will conclude this lecture where we're looking at external flow over bodies. What we'll be doing in the next segment, or in the next lecture I should say, is we're going to be looking at flow over multiple cylinders, and we refer to these as tube banks. If you recall, at the beginning we talked about cross-flow heat exchangers, and so that's what we're going to be moving into, looking at the fluid mechanics and the convective heat transfer for those types of configurations.